Hey, Arvind, how are
Sir,
you?
I'm fine, sir. How are you?
I'm good. I'm good. Krishna's coming in. Let me admit the others who are coming in.
Sure.
Okay. We have more people now. Hey, Samant. Hey, Krishna.
Hi, good morning.
Good morning. How are you guys doing?
Great.
Krishna, your voice is, I guess there is a lot of noise in the background.
Yes, sir. I am in hostel.
Okay, cool. Okay. So I guess I mean, I didn't plan much agenda today. So I just wanted to check in, and I guess um I was wondering like what we should do in the meetings, and in the poll it looked like people wanted to do robot dissection, like figuring out what is in a robot and things like that, which was kind of interesting. Um so I was thinking of picking a robot, but then I thought maybe we should do it in the group. So do you guys have any thoughts on, or like any particular robot that you want to kind of think through? I mean, again, this is not going to be any official kind of breakdown, right? Because we might pick up robots that we have not worked on, but it's kind of a thought process. Okay, let me add Jishnu as well. Hey, Jishnu. So this is kind of going to be a thought process where we'll try to predict like what components are in a robot, like what makes a robot, and then what they would have used. And so there are two parts to it. One is the hardware, the other one is the software itself. But in hardware, I mean the sensors and systems and things like that. And in the software, it would be like, okay, what are the components that would constitute the robot? So for this week, let's keep it just as casual as possible. Depending on how things go, maybe I'll make it a little bit more formal, like having um, writing things down or on a whiteboard or something like that. So, so any thoughts on any, or like any preference on any robots we should look into?
I was genuinely interested by the inner workings of industrial robotic arms. So
Industrial robotic
I
arms, okay? Mm-hmm.
I visited one of KUKA's service centers about
Mm-hmm.
3, 4 months ago, and I was
Okay.
really amazed by the inner components that were present inside there, even
Mm-hmm.
like 2, 3 decades old robotic arms. I never
Mm-hmm.
expected to see a lot of so much gears inside, so much complexity filled with
Yeah,
oil.
yeah. Mm-hmm.
So that
Okay,
was something that was much more complex than I imagined it to be.
I see. Yeah, yeah. Yeah, I think we can kind of try to figure out, start with that, like try to figure out what a robot arm would constitute, and then go from there. Any any objections to that?
I'm
Okay,
good. Yeah, we can go.
okay, let's go. So let me share my screen. So I just looked up KUKA arm, and just for people who are not familiar, this is kind of the arm that Sumit was talking about. Um, so it's kind of like they are one of the major producers of robotic arms. They've been in the field for a while. So they're kind of the big players in the field. And so I think maybe I'll talk about a couple of things that I know about these arms and what makes them kind of interesting. And maybe people can chime in and ask questions or correct me if I'm wrong, or mention other interesting things. Okay, so the first thing that comes to mind is like, okay, this is an arm. So, I mean, you could look at it. There are multiple joints here. So you could just put in multiple motors and then just get them do the stuff you want to do. But I mean, at least that's how I started. I thought about when I initially saw a robot arm, and in fact, like I was dumb enough to even try it with a couple of motors, and it turns out that it's not as simple as that. There is a lot of mechanics or like physics involved in the sense that I mean, the basic physics is if you pick up something and if it has a lever arm attached to it, what I mean by that is, let's say this is the just a pen, and I'm picking up the pen from here, and so if I add some weight to here, there is going to be a lot of torque on this end, right? So the longer this arm, the torque is going to be higher. So with a robot arm like this, you want to have a lot of torque on the on those areas which kind of like hold the lever arm. So that's why the base is generally like bulky, because it has these huge motors and gears and things like that. Um, so that's one of the fundamental things that makes these arms kind of special. And then about the gearing that Sumit was talking about. So you could achieve the level of torque two ways, right? One is you could put in a powerful motor that can do that, but there is a limit on how powerful that could be. The other thing you could do is like you can add gearing where you would trade off the speed with the torque. So that's what these kind of devices have. They kind of like do a lot of step down. They take a simple motor, but then they have a lot of gearing to um, step it down so that it can carry a lot of torque. So the downside with that, or like the challenge with that, is like if you keep adding a lot of gearing to increase torque, you would get the torque, but then you would decrease the speed a lot, right? So for example, in this robot, if you want to um, um, move at a certain rate, if you add a lot of gearing, then it's going to be like really slow, and that might not be sufficient in whatever application you have. So they have to have a trade-off. So if you look at these huge what is this called? Like the cranes that they use for construction. These cranes basically have tiny motors and not a lot of gearing. The idea there is you don't want them to be moving fast. You want the crane to be moving really slowly, because the faster you do, you create a lot of oscillations, and you don't want that. So they kind of uh, have everything moving at a slower pace. So in those scenarios, you could get a smaller motor with a lot of gearing, and could deal with that. But for industrial applications, you need to have the trade-off, and you have to have certain level of speed, and so for that you need to have certain level of power to the motor and the gearing. So that's kind of like the basics of like these devices. And then there is also the software piece of it, which is kinematics. So are you guys familiar with kinematics? Have you guys any tried kinematics? Okay, Arvind is nodding his head. Okay, I guess the rest are not familiar. So kinematics is basically the simple math of, I mean, you can think of it as like extended geometry, where you say that, okay, I have a particular, so I know where, or like, you know a coordinate frame, and then you want to know where a particular, the end effector of the arm would be. So for example, I mean, that's not, I didn't say that clearly. So let's say you know like where the base is, right? The base is fixed to the ground, and then you have your robot arm, the end effector, or the tip of the arm. You want to know where that is with respect to, like, all the joint angles that that your robot is using, based off of your encoder positions that you get. So kinematics basically figures out that, okay, given the base, given all the robot angles of the arms and then the length of the arm, I can use simple geometry to calculate where the end effector would be. Right. So you could use pure geometry for that, but it gets tedious after a bit because the kind of triangles that you draw. And then kinematics kind of gets you it gets you a little bit more and does it in a better way. It also accounts for the velocities. So that's kind of the difference between geometry and kinematics, where in geometry everything is static. You just use triangles to do that. Whereas in kinematics, you can also incorporate velocity in there. So that's kind of like what they generally use. But there's also something called inverse kinematics. Are you guys familiar with inverse kinematics? Have you tried that?
Yeah.
Okay, Arvind. And then who's the other person? Kishant. Okay. Hey, Kishant. So
Hello.
uh, so the inverse kinematics is the most interesting part, and that's what is generally used where given a position of the end effector or the robot arm tip, you need to figure out what joint angles will get you there. So that's kind of like um, it's kind of a harder problem because there are multiple solutions to that problem. Like there are multiple ways you can configure the arm to get that. I think maybe I should have a graphic at some point to kind of explain this. But it also gets you to degenerate cases and things like that. Anyway, so that's kind of like a harder nonlinear problem, and that's what you generally need to solve in an industrial application where you know that, okay, there is a particular part in a particular shelf, you need to reach out to grab it. So you need to know how to get your the tip of your arm to the shelf to grab it. So you'd use end effector to use the inverse kinematics to do that. So that's kind of like the math part of it and the software part of it. um so okay, that's my thing. I'll shut up now. I'll hear others talk about it. Any thoughts? Have any of you worked with robot arms before?
Yes, sir.
I've had a bit of experience there. Yes.
Oh, nice.
Yeah, same.
Uh, cool. So by I guess maybe I should ask one at a time. Like, can you just briefly explain like what kind of experience are like when you said work with it? Like, what does it really mean? What have you tried? I see Aravind on my list, on the top of the list. Let's start with Aravind.
So I had a nice experience working with the KUKA KR6 industry lab.
Mm-hmm.
So as we already discussed before, it was for a CNC automation process.
Mm-hmm.
And
Yeah,
this arm was basically used for the machine tending process. So
I
uh,
see.
this KR6 arm had a payload of 6 kgs. So this
Mm-hmm.
arm was able to pick up and tend to all the parts that a CNC machine would usually produce.
Mm-hmm.
So
Mm-hmm.
we were tasked with interfacing the arm's whole control with a software called Digimetrics, which would allow it
Mm-hmm.
to control the whole arm and its end effector from our PC.
Mm-hmm. I see. So did you have to do the kinematics and inverse kinematics for that?
No, KUKA usually performs their own inverse kinematics on their
Mm-hmm.
controller as such, but
I
we
see.
just need to give parameters such as the
Mm-hmm.
coordinates that we need to go to, along with
Mm-hmm.
other parameters such as status and turn, which determines which configuration we use to reach that position.
I see. Okay. Yeah, so one other thing I didn't talk about here is the dynamics of things, which is generally not a big deal in the ARM setup, but it becomes important when you're dealing with generally mobile robots. So dynamics is like, so when I talked about kinematics, I mentioned it includes velocity, right? Basically, if you look at the equation, geometry is just like dimensions and things like that. And kinematics is including time into the equation. So now we can know velocities. And then dynamics is you include mass into the equation. So you're saying that, okay, this arm is set up that this is this heavy. And then once you include mass into the equation, then you have momentum. So what that means is like when you swing an arm, you cannot stop it instantly. You need to account for the like how like there's going to be some momentum there, so you need to account for that, and say that, okay, this is not going to stop immediately. So if this is hit this heavy, then it should have this much momentum. So it means that it will take this much to dissipate the momentum to stop. So basically that kind of calculation comes in. So momentum, when you include the mass, it becomes even more complicated. And so you deal with that kind of things. As I said, like it's not a great deal for arms, but let's say you have like a tractor, like autonomous tractor, and you want to bring it to a stop, then dynamics would be an issue. Or if you want to make a like a heavyweight truck or something like that to follow a slalom course where you want to do like an S kind of pattern. Um, that's it gets harder because then when you try to turn, it would just drag you in a certain direction. So you need to bring in the dynamics to kind of say that, okay, how am I going to tune it to so that it follows this pattern as much as possible. So that's kind of like the where the dynamics comes into play. Uh, Sorry, I kind of like deviated there. Who else has worked on the robot arms?
I worked a bit with the Dobot arm for like a robotics competition. It
Uh-huh.
was also very
What?
basic. Like I did it like I think 3 years ago when I was in ninth grade or
Mm-hmm.
something. It was the
Mm-hmm.
very basic. It was just like the input coordinate and the output coordinate, and it has a z hop. But
Mm-hmm.
recently, I was doing some research on the math behind inverse kinematics, especially
Mm-hmm.
for multi-degree of freedom systems.
I see.
So
Like
yeah,
what?
so
Like
it's like the incremental. What is it? Incremental Jacobian inverse kinematics for
I see. Okay.
multi-degree of
So when you
systems.
say
Yeah.
multi-degree of freedom, like is it like a snake robot or what kind
No,
of robot?
like robotics arms only, but like let's say more than 3 degrees of freedom for in
I
three
see.
dimensional space like that.
Multiple
So
joints.
yeah, so you'll
I
have
see.
a lot of how to say a lot of orientations for the same end effector position.
Right,
So
right,
how
right.
do we get from one end effector position to another using
I see.
Jacobian matrices? And,
Mm-hmm.
yeah.
Yeah. Yeah, it gets a little harder. I mean, I kind of mentioned the high level bit, but then when you get into the math, it gets a little hairy, and it's not impossible, but it takes a little bit of time to get in there and deal with that. I guess one of the major things are like the things that you need to understand. Like two parts to it. The way I see it is like there is this high level math which says, okay, how are these things connected, and then the computation part, which is the Jacobian matrices, where you kind of like determine like what is the incremental, like if you want to make an incremental change, what I need to do, and then you use that thing to kind of apply um, um, to get to where you want to do. So that's where Jacobian matrices come in, and it needs a little bit of time devoted to study that, but it's kind of fun. Yeah. So who else said I think Suman said you worked on something related to robots?
Yes. My little experience is setting up robots. Those are shipped to the factory.
Mm-hmm.
Starting it up and installing, running already pre-installed software, and
I see.
then do
Okay.
the touch-up points.
Mm-hmm.
So I just worked on only KUKA,
Mm-hmm.
and make sure the robot has safe ops and other safety
Mm-hmm.
sensing
Mm-hmm.
and pretty much manipulation to pick or place a part, or yeah,
I see.
those
I
kind of
see.
things. Yeah.
So when
Um,
when you mention safety, is it like do they have a
they have
um
uh, a software and hardware integration called
mm-hmm.
SafeOp, and it interacts with various safety, like on the safety fans, whatever. We have the sensors for before we open or something to robot go in a it goes to zero or stalls right away. So then we do brake test on the joints. Yeah, to that level. Yeah.
I see. Yeah, so I was wondering, like, do they have anything like where you can design, where you can define the safe area you can operate on?
Yes,
Basically,
they
the
do
I
have.
see. Okay,
Yeah,
okay, yeah.
they do have, and there is other team member. He usually programs the Kuka equipment side virtually, and he uploads that data to create a map of safety
I
area
see.
perimeter in all the accesses. Yeah,
Yeah, yeah. That's interesting.
Kuka
So I
same.
get, yeah. So I think one other thing is like when we talk about robot arms, the thing that comes to our mind is generally these KUKA arms, which are like heavy industrial and all those things. But there are robot arms that are used in other areas too. Like for example, these Da Vinci robots that these are like the medical robots. You could think of them as um, robot arms as well, because they're kind of like doing the manipulation. And then even there you have these safety areas that you want to operate them on. You don't want the arm to go and hit another organ when you're operating on a certain organ. So yeah, kind of same principles apply there as well.
UI cobots,
Sorry?
something similar. Cobots like
Yeah,
UI
yeah.
from UI.
Yeah, yeah.
We use quite a bit for reliability testing to,
I see.
yeah, like simulate the customer behavior for
I see.
opening or closing. Yeah.
Mhm. Okay, cool. Nice. Anyone else?
Where I worked with ABB robots.
Oh, nice.
I did
Okay.
a rapid programming for that, and I'm actually learning right now. I'm in the course for industrial automation, of course, uh, and mostly we have done pick and place right now, and from tomorrow we'll start with welding actually, welding
Nice.
with the
Okay.
robots and.
So welding, you mean like using the robot to weld, or building the robot itself?
Yeah, using the robot to weld.
Nice. Okay. So what kind of arm are you using for that?
So for us right now we are using educational bots only. Like it's not present like ABB IR 1090, I guess, something.
I see.
Yeah, and this is for pick and place, and I don't remember the name of a welding robot. Uh, it's actually from
Yeah,
tomorrow we'll start with welding robot.
I see. Yeah, the like for welding and all those things, you need to have your accuracies dialed down a lot, right? So um,
If,
it it is kind of like a big thing for that. I mean, so one other thing I would like on a technical aspect is like the more the joints you have, the harder it gets to have a really stable end effector, because there is going to be a lot of or you have to get rid of all the jitter in each of the joints. And but I mean, if you're not going with, I mean, okay, so the more industrialized the arm is, they know how to control that, and they kind of make sure that the end effector is stable. But then if you get like a cheaper one, it's probably not taken care of. So when you have the end effector go to a certain location, you would see a lot of like a slight jitter in there. So so that's another thing that makes the robot arms complicated, because you have to kind of account for that as the number of joints increases. Oh yeah, backlash. That's another thing. That's so backlash. Thanks, Aaron, for pointing. So the backlash is basically when you have these like the gears, when the gears are meshing, they would you need to have like the perfect alignment, but there is going to be a little bit of tolerance to allow the gear to actually spin, right? Like if the gears are completely meshed in, you will not be able to spin it. So there's going to be a little bit of tolerance there. And what that means is that's going to have a little bit of backlash in the sense that you could move the thing a little bit, and then that would cause things to not be in a stable position, like in the sense that you set it to a certain location, but then you can go back and forth, and that causes the jitter as well. So backlash is one of major things in any geared system. You have to be careful with that. So we are building um, for a ground robot. We were building a autonomous drill, which would drill and pull the sample up, put it in a cuvette, which basically collects samples and then tests with a spectrometer. And it was designed in a simple way that it caused some backlash in the cuvette, or like the thing that collects the sample. So, and these cups are like just like 4 millimeters wide. So on the high level, if you see that, okay, it has a backlash that does not allow you to get the spinning mechanism to, let's say, 3 millimeters. That doesn't sound like a big deal, but then when your cup is just like 4 millimeter, and then you can have a 3 millimeter backlash, then it means that either you're dropping into the cup or not, right? So that's where things get like really complex, and you have to make sure that your backlash doesn't um, cause any trouble. Okay, cool. So I guess I talked enough today on robot arms and maybe confuse some people, and maybe I gave some incorrect information as well. I don't know. So anything else about the robot arm?
One very interesting thing that I usually notice is the different tires or speeds that they restrict you to. So with KUKA, what I experienced is that when you're usually teleoperating the robot, they limit you to about 250 millimeters per second. But then when you run the robot in automatic mode, which is only restricted to programmed movements instead of teleoperation, the speed is much, much higher. The movement accuracy while remaining in the sub-millimeter level is so fast that you would not be able to imagine that happening with such small arms.
So sorry, I missed the point. So you're saying what are they restricting on? Sorry.
Basically, to ensure safety in the industrial arms, because there is no such force sensing mechanism to detect collisions.
Right.
So they restrict the speed of the arm to different tires.
I see.
Okay.
Okay.
So when you're teleoperating the robot manually using the teach pendant, you're only limited to about a speed of
I
250
see.
millimeters per second. But then when you are programming the movements and you know that the robot is in a safe working environment, the speed is much higher, and that speed stays the same while maintaining sub-millimeter accuracy.
Yeah. I think that's a big deal, right? Like, and that's where the momentum comes into picture, right? So if you're operating at a faster pace, then you have a lot of momentum, and then if you have people around, they could get hurt, and that's the reason why they would restrict that. Yeah, that's an interesting point. Yeah. Okay, cool. So I guess maybe from next week we could I'll create a poll or something like that, and so we can decide on what robot we wanted to talk about, so that we can maybe prepare something and then and then comment out. I mean, talking on the fly is fine, but maybe if we prepare a little bit, maybe that will be a lot more useful. Okay, cool. So from next week, I'm thinking of pushing this thing to Saturday instead of Sunday. I have some personal commitments that I need to make, and I have to just run after this meeting every time. So maybe I'll pushing it to Saturday might make things better. So I'll do that, and also I I'm starting the Slack group setup, so I will send you guys invite for that, and then we can start communicating on Slack, as I mentioned in the other, like the previous email. Okay. Cool. Anything else we should talk today? Feel free to propose something that we should discuss, or like if you have any questions or anything like that, it's perfectly fine. So I guess maybe one thing we did last week was we said we will follow up on certain commitments. So Jishnu, I guess you committed to something. Did you get make progress on that?
Yeah, I'm
Okay.
audible. Not sure.
Yeah, I can hear.
Yeah, actually, I was going behind all the mapping algorithms. Like, what my
That's
commitment
cool.
was, like, for those who don't have context, I was trying to build a drone. Like, I'm just in the very starting stage.
Mm-hmm.
So previous week, I was dealing with uh, path following algorithms. I should
Mm-hmm.
say A star, RRT,
Okay.
and things like that. I
Mm-hmm.
didn't make much progress, but I was just trying to get things from the scratch.
Okay.
So
Well, that's important, right? Just starting is important. And once you get started, I think the momentum will push you forward. Okay. Cool. I think Krishna was on the line. I guess he dropped off. He was the other one who committed to something. We'll check with him next week then. Cool. Sumant, did you have something to say? I saw you unmuted.
No, I'm good. Yeah.
Okay. Cool. Okay. I think that's all I have for today. Maybe you can end early today, and let's meet next week. I'll send the details about the new. It's probably going to be the same time, but the day it'll be just Saturday. I hope you guys are okay with that.
Yes, sir.
Sure.
Okay.
Yeah.
Cool. Sounds good. See you then. Have a good rest of the Sunday for those who are in the US, but I guess in India it's already late at night. Okay. See you guys.
Yeah.
Bye.
Thank you.
Thank you. Bye.
Mhm.